Hello, this is Joseph Vadalero presenting the third lab of the Spring 2021 semester in Physics 2211. The goal of this lab is to observe and analyze the motion of a mass attached to an oscillating spring, using the file given to us from the video. We will then use a computational model to measure the energy change of the system while measuring the different types of energy, such as potential energy of the spring, gravitational potential energy, and kinetic energy. We will then compare the motion predicted by the model to the motion observed in the video. And finally, we will answer some final questions for this lab. Before we get into the actual lab, we need to understand some fundamental principles. The first of which being Newton's second law, which is seen here as velocity final is equal to velocity initial plus F net divided by mass multiplied by the change in time. Hooke's law is seen as the force of the spring is equal to the negative spring stiffness, represented by K, times the length of the spring, seen as S. The energy principle is delta E is equal to the change in kinetic energy plus the change in potential energy of gravitational and spring. The kinetic energy is seen as delta K is equal to 1/2 mv squared. Spring potential energy is 1/2 Ks squared. Gravitational potential energy, finally, is mgh, mass times gravity times height. And this is near the surface of the Earth. And since we are on the surface of the Earth, we can use this approximation. Going into Tracker, we can see that we used 0.7 meters as our calibration for this video. We got that from the video. We can also see that as the spring oscillates, seen in the graph and in the data, it has a period. That period we will calculate in the next slide. We can see that the spring oscillates here and continues to provide data in the X and Y direction. In order to move further in this lab and to have accurate glow script data, we need to do some calculations for the spring. First, we need to find the period, which is one oscillation. We find that by finding the time it takes for 3 oscillations and then dividing that by 3. Therefore, the period is 1.6144 seconds. This is the time it takes for one oscillation. The spring stiffness we have solved to be K is equal to 4 pi squared times the mass of the object all over the period squared. Since we already calculated the period in the previous step, we know that K is equal to 6.0892 Newton meters. Last thing we need to calculate is the relaxed spring length, which is seen as the magnitude of the force of gravity is equal to the magnitude of the normal force. This means that mg is equal to Ks. The relaxed length of the spring is equal to the magnitude of L minus mg over K. We got that from the previous step. And then once we calculate it, we can find that the relaxed length of the spring is 0.053 meters. Looking at our glow script code, we see that most of the equations come directly from fundamental principles. Some things to note here are that the mass of the ball comes from the video at 0.402 kilograms. The position vector comes from Tracker and is just the first point where time is equal to 0. We calculated the spring constant and the relaxed length of the spring on the previous slide. And in the while loop, while t is less than 9.497, that number just comes from our last data point in Tracker, where time was equal to 9.497 seconds. Another thing to note is updating our energy. All we do is take the energy at the moment and subtract the initial energy to find the change in energy. This will be very important when we see the graphs. Once we run the code and input the data from Tracker, we can see that the spring and that the motion of the system is very similar to that from Tracker and that from the video. While the X and Y position data is slightly off, this is likely due to the unaccounted drag force and other small forces and loss of energy. On to some final questions for the lab. The first, is the energy principle satisfied? In our computational model, we got this graph where the change in total energy is 0 the entire way. That is what we want for the energy principle to be satisfied. So for this particular computational model, the answer is yes. The final question asks us to estimate the period of oscillation using the x component and the y component. Due to the nature of the different components and the motion in each direction, the two periods of oscillation are different, although they are very similar.